Okay, so let me start then. So in the last class, we were talking about the last couple of classes, variations of energy, right? So we've seen two cases of the energy functional. So the first case that we looked at is for curves in a manifold, right? So the energy of a curve gamma is the integral over the interval of definition of the curve a to b of norm gamma prime t squared dt. There's a half also. Okay. And so for a curve, we looked at the curve, and then we looked at variations of the curve, keeping the endpoints fixed, right? Right. So there are actually two cases one can look at. So this is sitting inside your manifold M. Maybe M looks like this. So there are two cases. One is you look at so not necessarily closed curves. Then the variations that you look at gamma s mod s less than epsilon have fixed endpoints. Okay, so gamma s of a equal to gamma a, gamma s of b equal to gamma b for all s. Okay, so proper variations, as we call them. So then we have the formula for the first variation of energy, dds at s equal to 0 of the energy of gamma s is minus the integral a to b of the variational vector field v inner product with d gamma prime dt. Okay, where v is the variational vector field. This is del del s at s equal to 0 of gamma s. Right. So this is a section of Tm along gamma. So it's a section of gamma star Tm, right? Okay. Yes, this is clear. Okay, so
Yeah, it's clear.
And then there's another case, case B, where if you look at closed curves, then you can also look at variations which are also through closed curves. Variations gamma s through a family of closed curves. Okay. So variations by closed curves. Okay, so in this case, gamma s of A is equal to gamma s of B. And also you want the curve to be, so closed curves, well, actually you want it to be a map from a smooth map from the circle into the manifold, right? So here, what you want is that gamma A is equal to gamma B, and also gamma prime A is equal to gamma prime B. Okay. So that then you can extend it to a periodic function on all of R into the manifold, right? So for that, you need the derivatives also to match. Okay. And similarly here, you want the same for all the curves in the variation. Actually, you want all of the derivatives to match, not just the first derivative. You want it really to be a smooth periodic function on R restricted to the interval, restricted to a period, a fundamental period. Is that clear? Okay. So then again, you can check, you have the same formula for the variation, first variation of energy. This is again minus integral A to B in a product of the variational vector field with d gamma prime dt. Okay. All right. So in both cases, if I look at what's called a critical point of the energy functional, this means gamma such that the first variation is 0 for all variations of gamma, all admissible variations, right? So I should have drawn a picture. In the second case, you're looking at a variation where I'll just draw you a picture. You're looking at something like this. You have a closed curve, and then you're doing basically a free homotopy by closed curves. Okay, so these are the curves in your variation. All right. So they're all closed curves. Okay. This is the second case. So in either case, A or B, if I have a critical point of the energy functional, that means a curve gamma, so that for all admissible variations, the first derivative of the energy is 0. This happens if and only if gamma is a geodesic, right? So d gamma prime dt is identically 0, which means gamma is a geodesic. Okay. So critical points of the energy functional correspond to geodesics. All right. And similarly, if I look at, so I was looking at curves, now I look at functions on my manifold. So I have f from M to R, a smooth function. Okay. So again, there are two cases. So let me assume, yeah, I do need M is oriented. Riemannian manifold. So the two cases are, one is, say, M is compact. Okay, let me just assume M is compact in both cases. So the two cases are M has non-empty boundary or empty boundary. So the first case that we looked at last time was the boundary of M is non-empty. Okay, so then, for example, it could look something like this. It could be a manifold with boundary, which is, say, this could be M. This part is a compact oriented manifold with boundary. Okay, this could be M. And here you have your function f, taking values in R. Yeah. So in this case, the variations that you want fs by functions, these are constant on boundary n. Meaning that constant with respect to the parameter s. So that means that fs restricted to boundary m is equal to f restricted to boundary m for all s. Okay. So in this case, again, we computed the first variation of energy. And here what we found is that the first variation of energy was minus the integral over m of the inner product of, say, u with the Laplacian of f, dvol. Right, where u was the variational function. U was del s at s equal to 0 of fs. This was a smooth function on it. Okay. And the second case is if the boundary is empty, so for example, this whole genus 2 surface would be M. Then you can take any variation, any variation allowed. So any variation. So there's no restriction in this case. And you have the same formula for the first variation of energy. Okay, basically the formula for the first variation of energy is similar. I mean, the derivation is similar in all cases. You differentiate under the integral sign. Then you have to do an integration by parts. And because of the variations that we're looking at, from the integration by parts, you'll get some boundary term. That boundary term vanishes because of the variations that we're looking at. Okay. So in this last case where the boundary is empty, the boundary term vanishes because there is no boundary. Okay. You apply the divergence theorem to a manifold without boundary, the integral of a divergence is 0. Okay. Is that clear? Yeah, so F is a critical point of the energy functional if and only if, so the first variation of energy is 0 for all variations. Fs, and this is if and only if. From the formula for the first variation, you see that the Laplacian of F has to be identically 0. That means F is harmonic. Okay. So in both these cases, we see that both geodesics and harmonic functions, they arise as critical points of the energy functional. Is this clear?
Yes, sir.
Now what we want is a more general framework where we are going to look at maps between Riemannian manifolds. So now both the domain and the target are both going to be manifolds. Okay. So F is a map from a Riemannian manifold M to a Riemannian manifold N. Okay. So the first question is, how do we define energy, right? How do we define energy? So we want to define an energy functional, right, of for maps between Riemannian manifolds. So if you look at the earlier examples of curves and functions, you're taking the energy. So I didn't write this here. So the energy of F is half the integral over M of norm of grad F squared d vol. Right. So in both cases, even in the case of curves, the energy was the integral over the domain of the curve or the function of half the norm of the derivative squared, right? So for a map between manifolds, we want to define some norm of the derivative, right? So if I take a point P in M, so then what is df at P? This is a linear map from TPM, okay, to, so let me call this some vector space V. This is an inner product space V going to TFPN. This is an inner product space W. Okay. So now, suppose I have VW are inner product spaces. Okay. So then we can define on the set of linear maps from V to W. So VW are finite dimensional inner product spaces. So there is a natural inner product on the set of linear maps from V to W. So if AB are linear maps from V to W, right? Then I have their adjoints, right? A star, B star. They go from W to V, right? Okay. So we can define the inner product between AB. How can we define this? Any guess?
Trace of B star A or something.
Correct. Absolutely right. Trace of B star A, right? So actually, what is this inner product? Well, if I choose an orthonormal basis for V and for W, if I just choose an orthonormal basis for V, let me just choose an orthonormal basis for V, then B star A, this is an endomorphism of V, right? So for an endomorphism of V, the trace is going to be what? The sum over the diagonal elements with respect to that orthonormal basis. And the diagonal elements with respect to that orthonormal basis are B star A EI, inner product EI, right? Yes?
Yes, yes.
Okay, these are the diagonal elements. So this is the trace. And now the B star I can take to the other side. So this becomes sum over I. AEI, BEI, right? Okay. So now what is this? Well, if I choose, let's say, Fi is an orthonormal basis of W, then each AEI, this I can write with respect to the orthonormal basis Fi as sum over J, just the expansion with respect to the orthonormal basis, AEI inner product Fj into Fj, and then I have a sum over K, BEI inner product Fk into Fk, right? Yes? Yes?
Yes, sir.
Now, when I do a sum over Jk, what will happen? I'll get inner product Fj, Fk, right? Coming out. So that will be delta Jk. So then K has to equal J, right? So then I'll just get a sum over Ij, right? What will I get? I'll get this coefficient into this coefficient, right? Where K is equal to J. So I'll get AEI Fj inner product BEI Fj. Right? Now, what are these? These are nothing but the matrix coefficients of A and B with respect to the orthonormal basis EI and Fj, right? Yes? Is that clear?
Yes, sir. Fine.
Okay. So the point is, this inner product is just the usual inner product on R to the m cross n, right? Where you identify these linear maps with matrices using orthonormal bases. Okay, so this is independent of the choices of orthonormal bases. Is this clear? Okay. And so then what is the norm squared of a linear map? This will be just summation Aij squared, right? Is this clear?
Yeah, right.
Yeah, okay. Okay. So now we can come back and we can define, therefore, norm df squared as the trace of dfp star dfp, right? Is that clear? And now we can define, so we define what's called the energy density of F. So this is a function written E of F. This is half the norm of df squared. Okay. So this is a smooth function on M. Is this clear?
Yeah.
Okay. And now we define the energy of F. E of F is defined to be the integral of the energy density with respect to volume measure. Okay. So this generalizes the definition of energy to maps between smooth manifolds, right? You can see that in the special cases that we looked at of curves and of functions, this gives the same energy that we defined earlier, right? Is it clear? Okay.
When you are taking the integral, you mean EF at P default F, right?
Sorry?
I mean energy density of F at certain point P default.
Right. Yeah. What I mean, this EF is a function, right? So it's just the integral of this function with respect to the volume measure, the Riemannian volume measure. So, if you want me to write it, it's integral over M EF of X dvol M of X. I'm just omitting the dummy variable, right? Sometimes you write the dummy variable or you can write it without the dummy variable. It's the same thing. Okay.
Yeah.
It's just notation.
And the energy density, you defined it that way. Right?
This is a function. Yeah. So, okay, fine. So maybe to be specific, I should, but this is a function, right? Its value at P is the norm of half norm of dfp squared. Okay. This is a function. Okay. So is this all right?
Yes, sir. Yeah. Fine.
Yeah. Okay. Okay. So what we want to do is look at variations of F, compute the first variation of energy for maps between manifolds, and then we'll see what the corresponding critical points of the energy functional are. So as you've seen here, what we're doing is, for the case of the Laplacian, for the case of functions, the first variation of energy equal to 0, this leads to the Laplacian equal to 0. And Laplacian is what? It is trace of the Hessian, right? The Hessian is the second derivative for a map from a Riemannian manifold to R, right? So we're taking the trace of the second derivative, that equal to 0, right? That is giving us the critical points of the energy functional. Similarly, for a curve, for a curve, the domain, the tangent space is one-dimensional. So the trace is just this. So it's the one thing you have to be careful about. The second derivative here for a curve is actually this d gamma prime dt. this is vector valued. So you have to be careful what it means to say, what is the trace of a vector valued bilinear form? We'll talk about that. But this also you can think of as the trace of the second derivative. It's a vector in this case. It's not a scalar. That's all. There's a slight point to understand there. So we'll talk about that. Okay. So one might expect in the general case, right? So for a function like taking values in the real line, a scalar valued function, what is the second derivative? It's the Hessian, which you can think of as a symmetric bilinear form from the tangent space to cross tangent space to R, right? Now for a map between manifolds, we want to define the second derivative. It should be what? A symmetric bilinear form from tangent space of M cross tangent space of M to the tangent space of N of the target manifold, right? So it should be a vector valued bilinear function, right? Okay. So we have to understand how to define the second derivative of a smooth map. Okay. So, because as one might expect, in the first variation of energy, the term that should come up should be some sort of a trace of the second derivative. But the first thing to understand is what is the second derivative, okay? So that will be something called the second fundamental form. Okay, so let's start talking about that.
So is this a generalization of the Hessian?
Yes, yes, yes. This is going to be a generalization of the Hessian. Okay. So we just have less than 2 minutes left. So let me not start talking about it right now. I'll start in the next session. Are there any questions up to now? About variations of energy and so on? Any questions up to now? Okay. Okay, so there's just about a minute left. So let me stop this session and start a new one. Okay. So I'll stop this. We'll start a new session. Okay, so let's continue. Okay. So we want to understand what is the second derivative of a smooth map between Riemannian manifolds. So I have F from M to N. Smooth map. Okay. Now, DF at P, this is a linear map from TPM to TFPN. Yeah. So I can write this. A Hom of EF, remember, was identified with E star tensor F, right? So I can write this as I can identify this with TP star M tensor TFPN, right? Yes. Okay. Now, what is TFPN? This is a fiber of the pullback bundle, the pullback of the tangent bundle of N, right, under F. And this is the dual of the tangent bundle of M. So I can think of this as the bundle T star M tensor, the pullback bundle F star Tn, the fiber of this at P, right? Yes.
Yeah,
Is this
yeah,
clear?
right.
Yes. Okay. Now I want to differentiate DFP. So DFP, therefore, DF I can think of therefore as a section of this bundle, right? This is a section of T star M, the cotangent bundle or dual of the tangent bundle, tensor, the pullback of the tangent bundle of N, right? So this is what the first derivative is. I can think of it as a section of this bundle. Okay. Now what do I want to do? I want to differentiate this in any direction V in the manifold, right? So for that, I need a connection on this bundle, right? Now, I will have a connection on the tensor product if I have connections on each of the factors. So T star M is the dual of Tm. So on Tm, I have the Levi-Civita connection, right? So I can take the dual, the induced connection on the dual space, right? So there is a natural connection on T star M because it's the dual of Tm and Tm has its Levi-Civita connection, right?
Yeah.
Okay. Now, what about the connection on F star of Tn? Well, on Tn, the tangent bundle of N, I have the Levi-Civita connection of N, right? So what I want is a connection on the pullback of this bundle, right? So that, in fact, always exists. I mean, a natural compatible connection. So that is what's called the pullback connection. So let me just talk about the pullback connection. So suppose you have a smooth map between manifolds M to N, and say E is a vector bundle over N, over the target manifold with a connection nabla. Okay. Then you can define what's called the pullback connection on the pullback bundle F star E over M. Okay. So this is defined similarly to the notion of covariant derivative along a curve for a bundle with connection. Actually, covariant derivative along a curve for a section along a curve, that is a special case of a connection on the pullback bundle, where for a curve, what you do is you pull back the bundle by the curve. Okay, so you get a bundle over an interval. And the connection on that bundle over the interval is actually your covariant derivative along the curve. So the more general construction is this, a connection on a pullback bundle. So this is a definition proposition. It states the following. There is a unique connection nabla bar on the pullback bundle, which is compatible with the connection nabla in the following sense. So if I take any section S of E and I take any vector field X on M, then if I can look at S composed with F, right? So S is a section on E, which is a bundle over N. So I can compose it with F, right? At any point P in M, F of P is a point in N, and S of F of P makes sense as a vector in E, right? That is a vector in the fiber EFP. So S composed with F, this is a section of the pullback bundle, F star E, right? So my connection nabla bar will act on S composed with F, right? So what I want is the following compatibility, that this section on the pullback bundle, this comes from restriction of a section on N to the, right, by composition with a section on N. So the connection applied to this nabla bar X of S composed F, this should be given by, what you do is you take the image of X under DF. So that is a tangent vector in N. That tangent vector I can apply to this section S on N, right? Using my given connection nabla on E. And then I composed with F, okay? So what I would do is look at nabla dfx applied to S composed with F, okay? So I want this compatibility condition to hold between nabla bar and nabla, okay? So what that means is, for any point P in M and for any vector V in TPM, right? My tangent vector V applied to the section S composed F of the pullback bundle F star E. So nabla bar V of S composed F, this should be equal to the tangent vector DFPV applied to the section S of E on N. Okay, so this should be nabla sub DFPV of S. Is this clear?
Yes, sir.
Yes, is this okay for everyone?
Yeah, it's clear. Yeah.
Okay. So if you look at the definition for a second, you will realize that the covariant derivative along a curve of a section along a curve is a special case of this connection, right? Where the map F is the curve from an interval into the manifold, right? Covariant derivative of sections along a curve. What is a section along a curve? It is a section of the pullback bundle by the curve, right? Yeah, so covariant derivative along a curve is a special case of this pullback connection. Is that clear? Yes, can you see that?
Yeah.
Right, this compatibility connection is exactly what gave us the existence and uniqueness of the covariant derivative of a section along a curve, right? So, okay. Anyway, so let's prove the existence and uniqueness of this pullback connection. So first, like we did for the covariant derivative along a curve, we first prove the uniqueness. So suppose you have a connection nabla bar which satisfies this compatibility condition star. Okay. Then let me take any section S of the pullback bundle. Okay. So then what I do is I take an open set U in M such that U maps under F into an open set V in N, where V is such that we have a local basis S1 to Sk of the bundle E on V. Okay. Then, so V is a subset of N, U is a subset of M. So then on U, I can write my section of the pullback bundle S as a sum of coefficients AIs into SI composed with F, because the SIs are a local basis for E on V, right? Okay, and the AIs are functions on U in M, all right? Is this clear? Okay, so now if I take a vector field X on M, so then by the compatibility condition, on U, I can write that nabla bar X of S will be what? So this will be by linearity, sum over I, nabla bar X of AI into SI composed with F. Now, because this is a connection, this will act on, by the Leibniz rule, it will act on the function AI as XAI, and then you get into SI composed with F, plus you'll get AI into nabla bar X of Si composed with F. Now by the compatibility condition, this second term, nabla bar X of Si composed with F, this will be nothing but nabla dfx applied to Si, right? Is this clear? Yes. So that means I can express my connection nabla bar in terms of the connection nabla, right? And so nabla bar is uniquely determined by nabla. Is this clear? This equation means that nabla bar is uniquely determined on this open set U by this equation. And so therefore you get the uniqueness of nabla bar. Is that clear? Yes?
Yes, sir.
Okay. So now how do you get the existence? So my manifold N, I'm assuming is, well, we don't even need to assume compact actually. This works in non-compact case also. So you just cover N by an open cover V alpha such that on each V alpha, we have a local basis S alpha comma I goes from 1 to K. K is the rank of the bundle E. So on each V alpha, we have a local basis S alpha I. Then given this cover V alpha of N, you choose a appropriate cover U beta of M such that every U beta maps into some V alpha. Okay. So in fact, this cover U beta, you can just take U alpha to be F inverse of V alpha. This will be an open cover of N. Okay. So then on each U alpha, you define nabla bar on U alpha by this formula that we have above. Okay. This formula, where instead of this basis Si, we'll have the basis S alpha I. Right. So this defines a connection on U alpha. On F star E restricted to U alpha. Right. So that gives on each U alpha a connection nabla bar alpha, let's say, which satisfies the compatibility property star. Now, if I look at the intersection U alpha intersect U beta, then both the connections nabla bar alpha and nabla bar beta, they both satisfy the compatibility condition on the intersection. Therefore, by the uniqueness, which we already proved, nabla bar alpha has to equal nabla bar beta on the intersection. U alpha intersect U beta, right? That means that these connections on these open sets U alpha, they agree on the intersections. Therefore, they patch up to give me a global connection on the whole manifold M for the bundle F star E. Is this okay? Yes?
Yes, sir.
Okay. Any questions? Is this all right?
Yes, sir. This is fine.
It's fine. Yeah. Okay. So now we can define the second fundamental form, right? So we have the Levi-Civita connection on Tn induces a natural connection on T star M, and the Levi-Civita connection on Tn induces a connection on F upper star Tn, right? The pullback connection which we just described. Hence, we get a connection a natural connection on T star M tensor F star Tn. Okay. Is this clear? Yes. So, yes. Yes, go ahead. Yeah, question, go ahead. Yes, any questions? Someone was asking. Is this all right?
Yes, sir.
Okay, fine. So then we can define. So can define for P and M a linear map nabla df at P. So where does this go from? This goes from TPM to, so let me call this bundle for a second. Let me call this E, say. Okay. This is going to go from TPM to E sub P. Okay. What is this? V goes to. So note that DF is a section of E. So I can differentiate this section of E given this connection with respect to any tangent vector at P, right? So I can look at nabla sub V df, right? Yes? Okay. Yes?
Yes, sir.
So what is nabla df? This is called the second fundamental form. So let's understand what this object is. So nabla df, this is at each point, it gives me a linear map from TPM to E. So this is an element of the bundle HOM TM E, right? Okay. Now, what is HOM TME? This is equal to, I can identify this with T star M tensor E, right? Yes? Yes?
Yes, sir.
Now, what is E? E is T star M tensor F star Tn. So this becomes T star M tensor T star M tensor F star Tn, right? Okay. So what is this bundle? So the fiber is going to be what? T star M tensor T star M and then tensor this vector space. What that means is what? This is the bundle of bilinear maps from Tm cross Tm to F star Tn, right? So nabla df at P defines a bilinear map So this is the bilinear map that we were wanting. This is the analog of the Hessian. But this is now going to be a vector valued bilinear map. So nabla df at P, this goes from TPM cross TPM to TFPN. What is this? So this is V comma W goes to, so first of all, I can let V act on DF, right? So notice DF is a linear map from TPM to TFPN. It's a section of the bundle HOM TM F star TN. So when I differentiate this, right, I'll get another linear map, right, from TPM to TFPN. So this will act again on another vector W in TPM to give me an element of TFPN, right? Is this clear?
Yes, sir.
Okay.
Isn't the second term like grad phi TF of W, DF at W? Is it like D of F W comma V?
I'm sorry, what are you saying?
Like the terms, I mean the Nabla V DF at W. It is like D of DF at V comma W, something like that. Like Nabla V of F is DFP V transpose, right?
I don't understand what you're saying.
I am saying that for any vector V, the tangent space of M, so we have Nabla V of X.
What is X?
X is any smooth vector field on M.
Okay.
Then
So
that is
Nabla V
DXP
of X, Nabla V of X. Okay. Yeah, then what?
this is just DXP of V transpose, right?
What is V transpose?
DXP of V.
I don't understand. What are you saying? This is what? What is this equal to? No, what is this equal to? You're saying this is equal to DXP of V. That's what you're saying.
Yeah, DXP of V transpose, right?
Look, first of all, in the right-hand side, DXP is not well defined. There is no such thing DXP for a vector field on a manifold. What you have is Nabla X. This is what you have. This is a linear map from TPM to TPM. Okay, this makes sense. That's all you have. There is no such thing DXP. That only makes sense if your manifold is sitting inside Rn. Otherwise, this doesn't make sense. Okay.
I see, okay.
This doesn't make sense in general. There is no such thing DXP. I mean, there is one thing DXP, but that's a much more complicated object. If you want to look at that, X is a, look, you have to understand what objects are like. X is a map from M to TM, right? So if you want to look at its derivative, what will dx be? It will go from the tangent bundle of M to the tangent bundle of the tangent bundle of M. This is a much more complicated object. Do you understand?
Yes, sir. Yeah. Right.
This takes values in the double tangent bundle. That is the tangent bundle of the tangent bundle. So this is not what we want. What we want is this Nabla X. This is a map from TM to TM. Okay, we've reduced the dimension by half on this right-hand side. This is what we want. This Nabla X from TM to TM. Okay. All right.
Okay, sir.
Yeah, what you were saying makes sense if your vector field is sitting inside Rn. Okay. Then it is, you take dxp of V tangential component. not transpose, tangential component. That makes sense? Yeah, that makes sense if you're sitting inside Rn. That's correct. Yes. So you want to say whether something similar is true here?
Yeah, you was some sort of trying to correlate this.
Yeah, so then you would have to embed n into Rn and then take the tangential component.
Okay.
Yes, but you have to embed inside some Rn. Yeah. And there's no canonical embedding or anything, but
Yeah, I actually missed the term that A is sitting inside of it. Yes.
yeah, you have to embed it into Rn. Yeah. And then you can take the tangential component. That, yeah, I think that should give the same thing. Yeah, that should give the same thing. Yeah. Okay, so is the definition of the second fundamental form clear? It comes from the connection, the induced connection on the bundle E, which is T star M tensor F star Tn. Is that clear? Yes?
Yes, sir.
Okay. So what we want is to figure out how to actually compute this second fundamental form. So this is called the second fundamental form. Okay. So this is the second fundamental form. This bilinear map. Okay. Okay. So now I want to do a few calculations, okay, which will be useful for us. So suppose say EF are vector bundles over M with given connections, okay, with connections. Yeah. Now recall if alpha is a section of E star and S is a section of E, then and X is a vector field on M, then X applied to, so I can look at alpha composed with S, that will be a scalar valued function, right? So by definition of the dual connection, right, this X applied to alpha S, this was, this satisfied a Leibniz rule. This was nabla X alpha applied to S plus alpha applied to nabla X of S, right? Yes? Okay. Where be careful, this nabla X alpha, this is the induced connection on the dual bundle E star. And this nabla is the connection on the original bundle E. Okay. Fine. Is this okay?
Yes, sir.
Fine. Now let beta be a section of E star tensor F. So this is what we're looking at, right? Something like DF, that is a section of E star tensor F, right? Where E is TM and F is the pullback bundle F star of TN, right? So let's look at a section beta in E star tensor F. So then I can, this beta, it can act on a section S of E, right? Because the E star component will act on the S, and that will give you a vector in F, right? So then I can look at beta composed with S pointwise. This is a section of F, right? Okay. Yes.
Yes, sir.
So our claim is, this will be a very useful computation, that so this section of F, I can apply the connection on F to this, right? So nabla sub X of beta of S, the claim is this also satisfies the Leibniz rule. This will be nabla X beta applied to S, where this nabla of beta, this is the induced connection on the this tensor product, E star tensor F, okay? Plus beta applied to nabla X of S. Okay. See, the whole thing is what? The whole thing is a section of F. Okay. So it is different from this case, where in this case, this whole thing was a function on M. Now we're looking at something which is going to be a section of F. Is that clear? Yes? Is the difference clear?
Yes, sir.
Okay. So let's take local bases. Alpha I of E star and Fj of F. Let beta be sum over ij. I can write this as Bij alpha I tensor Fj, right? Because this alpha I tensor Fj, this will be a basis of the tensor product E star tensor F, right? A local basis of E star tensor F. Is this clear? Okay. Yes?
Yes, sir.
So then what will nabla X beta be? So by definition of the induced connection, so first of all, the connection is going to act on the functions. So there'll be a term coming from the functions X Bij, alpha I tensor Fj. And then the connection is going to act on this section of the tensor product, alpha I tensor Fj. So there again, we know that the induced connection on the tensor product, it satisfies the Leibniz rule. So I'll get two terms, one where you differentiate alpha I and one where you differentiate Fj, right? So this will give me plus Bij nabla X alpha tensor Fj plus Bij alpha I, sorry, this is alpha I here, tensor nabla X Fj. All right. Yes.
Yes, sir.
Okay. All right. Now, what is X acting on? Sorry, what is going to be nabla X of beta S? So this is going to be nabla X of So what is beta of S? Here the alphas are elements of E star and S is a section of E. So the alphas will act on S, right? So this is going to be sum over Ij, Bij, alpha I of S, and then that into Fj, right? Yes? So this is a scalar, this Bij into alpha I of S, this is a scalar, right? And this Fj is a vector in F, okay? Yes?
Right.
Okay, so now this nabla is a connection. This is a section of F. So by the usual rules for a connection, this will be sum over Ij by linearity and the Leibniz rule. So I'll have to differentiate this product of these two functions. So that I'll use the usual Leibniz rule for functions. So I'll get x Bij alpha I of S Fj plus Bij x of alpha I of S Fj plus a term where I differentiate the Fj, Bij alpha I of S nabla x Fj. Okay, so let me stop this session and start a new one. Okay, it's just less than a minute left. Okay, so let's continue with the calculation. Okay. So we have these three terms here. Now, this term here, x applied to alpha I of S, here alpha I is a section of E star, S is a section of E, sorry, S is a section of E. And so alpha I of S, this is a function. So x applied to this function, we can use the Leibniz rule that we have for the connection on the dual bundle, right? This original Leibniz rule, x of alpha S is nabla x alpha S plus alpha nabla XS. So we can use that down here. So we can expand this term into two more terms. So then what will we get? We'll get sum over Ij x Bij alpha I of S Fj plus Bij nabla x alpha I of S Fj plus I have this term here. Let me write this term here. Bij alpha I of S nabla x Fj. Okay. So if I look at, I have these three terms and then I have another term, sum over Ij. So I had this term nabla x alpha I of S. I'll also have a alpha I of nabla XS, right? So that would be a sum Bij alpha I of nabla XS Fj. Now, if you look at it, these three terms, this sum together, you look at the expression for nabla x of beta, then this sum is exactly what you would get if you apply nabla x beta to S, right? You would get these three terms and this sum here. Right, so this sum is nothing but nabla x beta applied to S. And this sum, as you can see, this is what you would get if you apply beta to nabla XS. Is this clear? Okay, so therefore this gives you nabla x beta of S plus beta of nabla x of S. Is this all right?
Yes, sir.
Okay. Okay. Fine. So now let's look at again at a map between manifolds F from M to N. So then DF is a section of okay, let me write it this way. So at any point P, DF at P, this is a linear map from TPM to TFPN. Now I can look at the adjoint of this. It's a map between inner product spaces. So the adjoint DFP star goes from TFP star N to, sorry, I'm taking for inner product spaces, so I won't have the stars. So I'll have, yeah, from TFPN to TPN. It just goes in the opposite direction. Sorry. Okay. So DF is a section of T star M tensor F star of Tn. Okay. Whereas what is DF star? So this is a, so this is what? This is Hom of, so this is the fiber of the pullback bundle, F star of Tn going to Tn, right? Now that is the same as F star of Tn dual tensor Tm, right? And that is the same as yeah, so I can leave it like this if you like, or if I can further write this as the pullback of T star N, F star of T star N, tensor Tm. Okay. So either way, both DF and DF star, these are in a sense, both are of the form sections of some bundle E star tensor F, right? Yeah. So I can use this Leibniz rule that I proved here for sections of bundles of the form E star tensor F. We can apply that to both DF and DF star, right? Okay. So so I have say here I have say M, and here I have say N. So let me take a vector field say Y on N, and I take a vector field X on M. So then I can look at DFX. That's going to be a tangent vector at points of N. DFX will be a section of the pullback bundle F star Tn, and I can look at Y composed F, right? Okay. So what am I doing? I'm looking at X. Yeah, X is a vector field on M. Y is a vector field on N. Okay. And let me take another vector field Z on M. Okay. Then I can look at Z acting on the inner product of DFX with Y composed with F, right? Yes. Yeah, this inner product is a function on M. So Z acts on this function. Is this clear? Okay. Yes. So by the metric compatibility, this is going to be given by a sum of two inner products, Z acting on this. So see, dfx is what? dfx. This is a section of my f star Tn, right? So Z can act on this, right? So this is going to be inner product of nabla Z of df of x, inner product with y composed with f, plus inner product dfx with nabla Z of y composed with f, right? Yes?
Yes,
Yes,
sir.
sir.
Okay. Now I can use the property that we just proved. This nabla Z applied to df of x. This is of the form beta composed with s, right? So I can use the property that we just proved. This is going to be equal to the nabla Z df, okay, acting on x plus df acting on nabla zx, inner product with y composed with f plus inner product df x acting on nabla z y composed with f. And I can, so this nabla z df, this is a linear map from TPM to TFPN, right? So this linear map, I can take its adjoint and move it to the other side also. Okay, so this is going to be inner product of x with nabla z df star of y composed with f. Yeah. And yeah, plus I'll have these other two terms, df of nabla zx y composed with f plus dfx nabla z y composed with f. Okay, now let me do the same calculation in another way. So this z inner product dfx y composed with f, this I can write as z acting on inner product of x with df star of y composed with f, right? So what is that going to be? Now I use the Leibniz rule again. This is going to be nabla zx inner product with df star of y composed with f plus inner product of x with nabla z of df star of y composed with f. Okay. So this first term here, I can move the df star over here. So this is going to become inner product of df of nabla zx, inner product with y composed with f. Okay, so you can see that this term is the same as this term above here. Okay, so when I equate these two will cancel. And then from here, I'll get two other terms. Again, using, this is of the form nabla z of beta composed with s. So for beta composed with S, I'll get again a Leibniz rule. I'll get two terms, right? So one will be nabla Z of df star acting on Y composed with F, inner product with X, plus I'll get another term df star acting on nabla Z of Y composed with F, inner product with X. So now this term, I can take the df star to the other side, and then this term becomes the same as this term above here. And this first term becomes the same as this second term above here. That means that this term and these two terms are equal. So when you equate things, what you will find is that the inner product of X with nabla Z df star of Y composed F, this is the same as the inner product of nabla Z of df star acting on Y composed with F, inner product with X. Okay, so this is true for all X, right? So if the inner product of with all X is the same, then that means these two vectors must be the same, right? Yes. If two vectors have the same inner product with all vectors, then they're equal, right?
Yeah.
So that implies what? That implies that nabla Z df star of Y composed F is equal to nabla Z of df star acting on Y composed F. Now this is true for all Y in chi-n, right? So that will imply that these linear maps, nabla Z df, the adjoint of this linear map is equal to the covariant derivative of the adjoint map df star. Okay? Is this clear?
Yes, sir.
Okay, so this is what I wanted to prove. So we've done this computation. Okay, fine. So we're getting there. We're getting there. So now, yeah, okay. Right. So there are a few more computations. Maybe I'll switch to the notes. It'll be faster. So one is the symmetry. We can now prove that the second fundamental form is symmetric. So let me do that. We'll need that. So yeah, so we can now prove that the second fundamental form is symmetric. So that is, this nabla df was a bilinear map, right? So it acts on a pair of vector fields xy in chi-n. So this is going to be the same as nabla df acting on yx. Okay, so this is a symmetric bilinear map. So to prove this, we will actually use symmetry of the Hessian. So how do we do that? So let u be a smooth function on n. So then if I take a vector field x on n, so then I can look at if u is a function on n and f is a map from m to n, I can compose u with f, right? So u composed f, this will be a function on m. Okay, so its gradient vector field, this will be a vector field on m. That I can take the inner product with x. Okay, now by definition of the gradient vector field, this inner product with x is the same as the vector du, d of u composed with f acting on x, and that is the same as du composed with df of x by the chain rule. And what is du acting on df of x? This, by the definition of the gradient vector, this is grad u at the point f of x, inner product with df of x, right? And here, this df I can move to this side. I want to write everything as an inner product with x. So then I move it to the left-hand side. This becomes df star of grad u composed with f, inner product with x. So now this is true for all vector fields x, right? Inner product of grad u composed f is inner product of df star of grad u composed with f. Inner product with x is the same. So since this is true for all x, these two vectors must be the same, right? So therefore we get a formula for the gradient of a composition. The gradient of u composed with f, this is df star of grad u composed with f. Okay, is this clear? Okay, so now let's compute the Hessian of u composed with f. Okay, so if I take two vector fields x, y on n, so let me look at the Hessian of u composed with f acting on x comma y. So by definition, what is this? This is the inner product of nabla x of grad of u composed with f acting on y. But grad of u composed f, this is df star of nabla u composed with f. So nabla x of this, again, this is of the form beta composed with s, right? So nabla x of this will satisfy the Leibniz rule. So this will be nabla x of df star acting on grad u composed with f plus df star acting on nabla df. So yeah, so when nabla x acts on this composition, by the definition of the pullback connection, this will be nabla dfx acting on grad u. Okay, yeah, by definition of the pullback connection. And now we can use the fact that nabla x of df star, this is equal to nabla x of df whole star, right? This is what we just proved. Yeah, so this is going to be nabla x of df whole star acting on grad u composed with f plus df star acting on nabla dfx of u inner product with y. So now the adjoints I can move on to the other side, onto y. So then I'll get grad u composed with f inner product with nabla x df acting on y plus nabla dfx u inner product with df of y. Okay. Oh, sorry, there's not u here. It's a grad u. There's a grad missing here. There was a grad u here. Sorry, there's a grad u and a grad u here. That's a typo. There's a grad u missing here and a grad u missing here. So what is this? This nabla x df acting on y, this by definition, this is the second fundamental form. Nabla df acting on xy, right? This is the second fundamental form, nabla df acting on xy. So we get the inner product of this with grad u composed with f, plus what is this term? There's a grad u here. So this by definition is the Hessian of u acting on dfx dfy, right? Okay. Now look at the left-hand side and the right-hand side. This left-hand side is symmetric in x and y because it's the Hessian of a function u composed with f, right? And we know the Hessian is symmetric, right? We've proved that. So the left-hand side is symmetric in xy. Now look at the last term here. The last term is the Hessian of u acting on dfx dfy. So this is also symmetric in xy, right? Because the Hessian of u is also symmetric, right? So since the Hessian of u composed f and the Hessian of u are both symmetric, it follows that this term is also symmetric in xy, right? So what we get is that grad of u composed with f, inner product with nabla df xy, this is the same as grad u composed with f, inner product with nabla df yx, right? This term is also symmetric in xy. All right, so this is true for all smooth functions u on n. From that, it's easy to see. You can choose this grad u at a point f of x to be any tangent vector in n that you want. So this is true for all tangent vectors in n. And therefore you get that nabla df of xy is equal to nabla df of yx. Is that clear?
Yeah, it's clear.
Okay, so we're just using the fact that the Hessians of U composed F and U are both symmetric. That's all. Okay, so symmetry of the second fundamental form, it follows from symmetry of the Hessian. Okay. All right. So now we have this symmetric bilinear map, the second fundamental form. So we can look at its trace. So how does one define the trace? Okay. So one can define the trace of a symmetric bilinear map on an inner product space as follows. So first of all, let V be a finite dimensional inner product space. Okay. So then any symmetric bilinear form B from V cross V to R, this corresponds to a self-adjoint linear map T from V to V, right? Such that B of VW is inner product TVW, right? So then you define the trace of this symmetric bilinear form B to be the trace of this self-adjoint linear map T, right? So what is this trace? This is the sum of the diagonal elements, inner product TEI with EI, where EI is any orthonormal basis of V, right? And this TEI inner product with EI, by definition, this is B of EI. Okay, so therefore the trace of a symmetric bilinear form, a function, is just the sum over I B of EI for any orthonormal basis EI of V. Is this clear? This is the trace of a symmetric bilinear form, all right? Yes?
Yes, sir.
Okay, now similarly, how do we define the trace of a vector valued bilinear map? So suppose W is a finite dimensional real vector space, and let B tilde from V cross V to W be a symmetric bilinear map, right? So then we define the trace of B tilde to be the sum over I, B tilde of EI comma EI. So this is now an element of W. This is a vector, okay, where EI is any orthonormal basis of V. So what you have to check is that this is independent of the choice of orthonormal basis. So that is not hard to see. If I take any orthonormal basis Fi, right, or not any other orthonormal basis of V, what you can do is you take an element alpha of the dual of W, okay, in W star. Then if I look at alpha applied to this sum over I, B tilde Fi, by linearity, this is the sum over I, alpha composed with B tilde of Fi comma Fi, right? But now alpha composed with B tilde, this is a scalar bilinear map, right? It's a bilinear function. So the sum Fi for this alpha composed with B tilde, this is by definition the trace of alpha composed with B tilde, right? But now the trace of alpha B composed with B tilde, I can also compute using the orthonormal basis EI instead of Fi, because this is a scalar bilinear function, right? So this is also sum over I alpha composed with B tilde, EI comma EI. And this, again, I take the alpha outside. This becomes alpha of sum over I, B tilde, EI. Now, since this is true for all elements of the dual alpha, it follows that the vectors inside are equal. So therefore, sum over I, B tilde, Fi is equal to sum over I, B tilde, EI. Is this clear? Yes?
Yeah, it is fine.
Yeah. So therefore, the trace of B tilde is well defined. Okay. And this satisfies that if I take any element of the dual, alpha, in W star, then alpha of trace B tilde is trace of alpha composed with B tilde. Okay. So now we can finally define what's called the tension field of a smooth map. So definition. The tension field of F, this is going to be given by taking the trace of the second fundamental form. So the second fundamental form, it takes values in what? In the bundle F star Tn, right? So the trace, when I take the trace, it's going to be also an element of F star Tn, right? So that means the second, the tension field of F, this is the section tau F. So this is a section of F star Tn defined by tau F at P. This is defined to be the trace of nabla df at P. So this is an element of what? TFPN. So this is a vector field along F, okay? Is this clear? So explicitly, what is this? This is going to equal the sum over I nabla df P of EI comma EI for any orthonormal basis EI of TPN. Is this clear? Okay. Yes.
Yeah, it's clear. Yeah.
So this is similar to the Laplacian, right? In the sense, the Laplacian was trace of the Hessian, right? So the Hessian was what? It was the symmetric bilinear function nabla squared f acting on EI comma EI, right? So instead of nabla squared f acting on EI comma EI, here you have nabla df acting on EI comma EI. That's all, right? So in fact, we'll show later that you can actually compute this as the Laplacian of f composed with the inverse of the exponential map on n. That's a computation we'll do next time maybe. Today, I just want to finish by computing the first variation of energy, and you will see that this tension field, this plays the role of the Laplacian which came up in the first variation of energy for functions. Instead of that, you'll get the tension field appearing here, okay? So let's just finish today by computing the first variation of energy, okay? For a map between manifolds. Okay. All right. So the tension field is the trace of nabla df. Okay.
I just have a question.
Yes.
What is the Laplacian of a map? Is it some sort of a trace
No.
again? Or-
No. So yeah, okay. So I did mention that. Actually, what happens is, see, no, if so, okay, fine. So I have let's say a small ball in M. This maps into, let's say, some other small ball B prime in N, which is a geodesic ball in N, let's say. So this is P, this is F of P. Now what I can do is I can take the inverse of the exponential map, X F of P inverse. So this is, you think of this as a logarithm, right? It's the inverse of the exponential. It goes from a geodesic ball into the tangent space TFPN, right? Okay, now this is a vector space. This is a vector space, right? Yes.
Yeah.
Okay, now for a map which takes values in a vector space, you can define its Laplacian by taking the Laplacian coordinate wise. Okay, you choose some coordinates on the vector space. It doesn't matter what coordinates you choose. And then you just take the Laplacian of the coordinate functions, right? So for example, if you have a function taking a map taking values in Rn, then you can define its Laplacian. If its coordinates are f1 to fn, the Laplacian of f will be just the vector Laplacian f1 up to Laplacian fn. All right.
Yeah. Okay.
Okay. So similarly, you can define the Laplacian of a vector valued function. Okay. So I can look at so the Laplacian will be an element of this vector space, right? So what I look at is I look at x fp inverse composed with f, right? So this is a vector valued function. Now I take the Laplacian of this at the point P. So this is a vector in TFPN. This vector equals the tension field tau FP. Okay. So this is the formula I was mentioning. We'll prove this next time. Okay. Does this make sense?
Yeah.
So this tension field is sort of a nonlinear Laplacian. It's the Laplacian of the logarithm of f. All right. It's the Laplacian of log f. So the nonlinear part is in the logarithm. That's a nonlinear map, right? So is this okay? We'll prove this next time. This is only true at the point P. This is not true at other points near P. This is only true at the point P. Okay. Okay, so I don't think I'll have time. Will you give me just 5 minutes after this session? I'll finish the computation of the first variation of energy, just so that you see where the tension field is coming from. Okay.
Yeah. It's okay.
Okay, so when this session finishes, I'll just start another session for 5 minutes. Okay. I'll just finish this first variation of energy. Okay. So we have a smooth map between Riemannian manifolds, which are compact without boundary. So a variation of f is the usual thing. It's a smooth map from an interval minus epsilon epsilon cross m into n, right? So that f0 is f, where ft of x is f of t comma x. Okay. So then you can define the variational vector field v. This is going to be a vector field along f. In other words, a section of the pullback bundle f star tn. V of x is the usual thing, del del t at t equal to 0 of ft of x. So this is an element of the tangent space tfxn, right? Now, if I take a vector v in TPM, then if I look at dft of v, right, this gives me a vector field along a curve ft of x, right? dft of v, this is a element of the tangent space at ft of p, right? So ft of p is a curve in n as t varies. So I can take the covariant derivative of this vector field along the curve, right? So I look at capital D del t at t equal to 0 of dft of v. Now dft of v, I can write as del del s at s equal to 0 of ft of gamma s, where gamma is any curve such that gamma 0 is p and gamma prime 0 is v. Now I can use, so I get a parametrized surface ft of gamma s. Now the property which follows from symmetry of the connection means I can interchange this capital D del t with this del del s. So this becomes d del s at s equal to 0 of del del t at t equal to 0 of ft of s, and del del t at t equal to 0 ft of gamma s. This is v of gamma s. And when I'm taking the covariant derivative d del s of v of gamma s, this is going to be nabla sub v of v. Okay. Okay. So this means if I take the covariant derivative of these differentials dft, what I get is the section nabla v of the bundle T star M tensor F star N, F star Tn. Okay. So let me stop this session and start a new one just for 5 minutes. Okay.